Students, in this session, we will begin Project 2, Principles and Equipment of Special Processing Technologies, which will open a door to a realm different from traditional metal cutting processes. Special processing refers to methods that utilize energy forms such as electrical energy, thermal energy, light energy, electrochemical energy, chemical energy, and acoustic energy for machining. This breaks the limitations of traditional cutting processes that rely on mechanical energy, enabling the completion of many tasks that are difficult for conventional machining. Next, let's delve into the detailed knowledge of special processing. In traditional metal cutting processes, material removal primarily relies on mechanical energy through direct contact between the tool and the workpiece. However, with the advancement of modern industry, many hard-to-machine materials, such as hard alloys and titanium alloys, are being widely used. At the same time, there are increasing demands for precision, surface quality, and complex shapes of parts. Traditional machining methods are gradually becoming inadequate in these areas. It is against this backdrop that special processing has emerged. Special processing refers to methods that utilize energy forms such as electrical energy, thermal energy, light energy, electrochemical energy, chemical energy, and acoustic energy for machining. It does not rely on mechanical energy, but instead directly uses these energies to remove or add material, achieving the machining of parts. This approach transcends the limitations of traditional processing, offering more possibilities for modern manufacturing. 1. Overcoming hardness with softness. Special processing allows for the machining of hard materials using soft tools, and it can even process materials with extremely high hardness and strength. For example, electrical discharge machining (EDM) uses high temperatures generated by pulse discharges to erode metal. The electrode material can be relatively soft, such as graphite or copper, yet it can machine materials with high hardness, like hardened steel and hard alloys. This breaks the conventional notion in traditional machining that the tool must be harder than the workpiece, embodying the characteristic of overcoming hardness with softness. 2. Non-blade cutting special processing does not require traditional cutting tools and does not involve significant mechanical cutting forces. For instance, laser processing uses a high-energy density laser beam to irradiate the workpiece, causing the material to melt or vaporize instantly for removal without direct contact or cutting force between a tool and the workpiece. This non-blade cutting method avoids workpiece deformation and vibration caused by cutting forces, ensuring machining precision and surface quality. High machining precision and surface quality special processing can achieve very high machining precision and surface quality. For example, electron beam machining can reach micron-level precision 5 to 20 μm, meeting the demands for high-precision micro-holes and narrow slits. Additionally, since there are no mechanical cutting forces during the process, the workpiece surface does not experience residual stress or work hardening, significantly enhancing surface quality. 4. Ability to machine complex shaped parts. Special processing can machine parts with various complex shapes, especially those with intricate structures and special contours. For instance, wire-cut electrical discharge machining (EDM) can control the movement path of the electrode wire through a CNC system to produce complex two-dimensional and three-dimensional shapes, such as mold cavities and impeller blades. 1. Electrical discharge machining (EDM) principle. Electrical discharge machining utilizes high temperatures generated by pulse discharges to erode metal. During the machining process, the tool electrode and the workpiece electrode are connected to the two poles of a pulse power supply and immersed in a working fluid. When pulse voltage is applied across the electrodes, the working fluid breaks down at the point of minimum gap between the electrodes, forming a pulse discharge channel. This generates instantaneous high temperatures exceeding 10,000 degrees Celsius, causing the metal material on the workpiece surface to melt and vaporize, thereby being eroded away. Application: electrical discharge machining is widely used in fields such as mold manufacturing, aerospace, and electronics. For example, in mold manufacturing, EDM can machine various complex-shaped mold cavities, such as those for plastic molds and die casting molds. 2. Laser machining principle. Laser machining uses a high-energy density laser beam to irradiate the workpiece, causing the material to melt and vaporize instantly for removal. The laser beam is focused on the workpiece surface through a focusing system, forming a very small spot with highly concentrated energy. This causes the material to heat up rapidly, melt, and vaporize, with the resulting vapor being ejected at high speed, thereby achieving material removal. Application: laser machining is widely used in fields such as automotive manufacturing, electronics, and aerospace. For example, in automotive manufacturing, laser cutting can be used to cut sheet metal for car bodies, offering advantages such as fast cutting speed, high precision, and good cut quality. 3. Electrochemical machining (ECM) principle. Electrochemical machining removes metal by utilizing the principle of anodic dissolution. During the machining process, the workpiece serves as the anode and the tool as the cathode. A direct current is passed between the two electrodes, which are immersed in an electrolyte. Under the influence of the electric field, metal atoms on the surface of the anodic workpiece lose electrons and become ions, entering the electrolyte, thereby achieving material removal. Application: electrochemical machining is commonly used for the mass production of complex surfaces, such as integrally bladed rotors and compressor blades in the aerospace industry. For example, in the machining of aerospace engine blades, ECM can ensure the precision of the blade profiles and the surface quality. 4. Ultrasonic machining (USM) principle. Ultrasonic machining utilizes the end phase of a tool vibrating at a high frequency 20 to 40 kHz to produce hammering and micro-cutting actions in an abrasive containing liquid medium, achieving the micro-removal of hard and brittle materials. The high-frequency electrical oscillations generated by the ultrasonic generator are converted into ultrasonic vibrations by a transducer, and the amplitude is then amplified by a horn. causing the tool to vibrate at high frequency and impact the abrasive particles, thereby machining the workpiece. Application: ultrasonic machining is suitable for processing hard and brittle materials such as glass, ceramics, and quartz. For example, in the processing of optical glass, ultrasonic machining can achieve high-precision cutting and drilling operations. 1. Aerospace field. In the aerospace field, special processing technologies are widely used in the manufacturing of various critical components. For example, the blades of an aircraft engine are one of its core components, characterized by complex shapes and extremely high requirements for precision and surface quality. By employing special processing methods such as electrical discharge machining (EDM) and electrochemical machining (ECM), the profile, precision, and the surface quality of the blades can be ensured, thereby enhancing the performance of the engine. 2. Electronics and information field. In the electronics and information field, special processing technologies are used to manufacture various micro-nano structures and electronic components. For example, laser machining can be employed in the production of integrated circuit chips, achieving high-precision photolithography and etching processes. Additionally, electron beam machining can be used to manufacture micro-nano sensors and micro-electromechanical systems (MEMS). 3. Mold manufacturing field. In the mold manufacturing field, special processing technologies are indispensable. For instance, electrical discharge machining (EDM) can machine various complex-shaped mold cavities, such as those for plastic molds and die casting molds. Laser machining can be used for surface treatment and repair of molds, enhancing their service life and surface quality. The development of special processing technologies fully embodies the spirit of technological innovation that breaks conventional thinking. Traditional machining methods encounter bottlenecks when dealing with hard-to-machine materials and complex-shaped parts. In contrast, special processing technologies, by utilizing different forms of energy, have overcome the limitations of traditional machining. They achieve solutions such as soft overcoming hard and bladeless cutting, which are challenges that traditional methods cannot address. This inspires us to dare to break through mental limitations in our studies and work, to boldly challenge established paradigms, and to seek new methods and approaches to problem solving from the fundamental nature of things. Only in this way can we drive technological progress and societal development. In this lesson, we learned about the principles and the equipment related to special processing technologies. We first understood the concept and background of special processing, which developed as traditional machining struggled to meet the demands of modern industry. We then explored the characteristics of special processing, including soft overcoming hard, bladeless cutting, high machining precision and surface quality, and the ability to process complex-shaped parts. Next, we introduce the classifications and principles of special processing, such as electrical discharge machining, EDM, laser machining, electrochemical machining, and ultrasonic machining, and illustrated their significant roles in fields like aerospace, electronics and information, and mold manufacturing through practical application cases. Finally, through the development of special processing technologies, we appreciated the importance of the spirit of technological innovation that breaks conventional thinking. I hope that in your future studies and work, you will be courageous in innovation and continuously explore new knowledge and technologies.